Systems 2021. The theme of this year's IEEE International Conference on Industrial and Information Systems is Deep Learning for Deep Understanding. Accordingly, this post-conference tutorial is focused on explainable machine learning, which has been one of the most trending topics. To the best of our knowledge, we are discussing this topic at a platform like this for the first time. Today's tutorial will be focused on introducing the methods for the explainability of machine learning models, giving hands-on experience on the tools, and discussing prospects of applications of the introduced methods. To start off the event, first, let me introduce the resource persons for the tutorial. Dr. Kasun Amarasinghe is a postdoctoral research associate at Carnegie Mellon University, working with Professor Wright Ghani. Prior to joining CMU, he received his PhD in computer science from the Virginia Commonwealth University in 2019, and his BSc honors in computer science from the University of Peradeniya in 2011. His current research lies in the intersection of machine learning and public policy. And his research interests include machine learning-based decision support systems, their societal impacts, and their interpretability. Sir, it's with great honor I welcome you to this event. Moving on to our next resource person, Dr. Damayanti Herath, graduated with a BSc Honours in Computer Engineering from the University of Peradeniya in the year 2012 and is a member of IEEE. She was a member of the Optimization and Pattern Recognition Research Group of Melbourne School of Engineering, Australia, where she worked on computational models and methods to profile inherently diverse DNA sequencing data which encode genetic information of multiple species and organisms. He is currently a senior lecturer at the Department of Computer Engineering, University of Peradeniya. Her research interests are in applied machine learning, especially in areas with social impact. Madam, it's my pleasure to welcome you today. Mr. Shyaman Jayasundara received the BSc degree in Computer Engineering from the University of Peradeniya in the year 2020. He is currently a full-time research assistant at the Agricultural Biotechnology Center at the University of Peradeniya. His research interests include machine learning applications in bioinformatics and health informatics. Mr. Shyaman Jayasundara, it's our pleasure to have you here today. Lastly, I would like to welcome our final resource person for today's event, Mr. Amila Indikar, who graduated with a BSc Honours in Computer Engineering from the University of Peradeniya in 2020. He is currently employed as a lecturer on contract at the Department of Computer Engineering, University of Peradeniya. His research interests are in applied machine learning, time series analysis, and mathematics. So without further ado, I would like to invite Dr. Kasun Amarasinghe to take on the platform. Over to you, sir.
Thank you very much. Thank you very much for that great introduction. It's great to be back at Peradeniya, albeit virtually. Would have been great to be in person, but such is the world. Today, let me quickly share my screen. I think the host will have to give me screen sharing to share the slides. Whoever is hosting, if you can give me sharing rights to share my screen, to share the slides, that'll be great. Thank you.
Give me a second, Kasun.
Yeah, and while we wait for that, I guess I feel like attendees are slowly coming in. It's early morning, if I'm not mistaken, over there, so it's not the ideal time to be listening to someone drone on about explainable machine learning. We'll do a bit of housekeeping while we get set up the technical stuff. Please feel free to stop me and ask questions anytime as this thing is going on. We'll take turns in presenting. I'll take the first section, and then Dr. Herat, Ms. Jasper, and Mr. Indika would take the second half, and then we'll have another discussion. So hopefully this 2 hours would be very fruitful, and hopefully it'll open up some doors and some research areas as well. Let me try it now. Okay, fantastic. So now I hope all of you can see my screen.
Yes.
Great. Yeah. So as she mentioned, it's the tutorial is explainable machine learning, and I'm a postdoc at Carnegie Mellon. I work on mostly on applied machine learning in the sector of public policy, where we use machine techniques to solve societal problems with societal impact. And interpretability or explainability is a very crucial component of that, because we are making decisions about human lives. So we need to know what the model is learning, how the model is making decisions. And I'll be joined today by Dr. Herat, Mr. Indika, and Mrs. Asundara in doing this. For this, I have an assumption that all of you are generally familiar with machine learning and machine learning techniques. You don't have to be an expert in the field, but it would be beneficial to have some idea about what classification is, what regression is, what like the basic approaches to machine learning, and what sort of problems that we can solve using machine learning. And hopefully by the end of this session, if you are coming in with that initial knowledge, hopefully we can give you a general appreciation about how important explainable machine learning is, and when and how it can be useful. And hopefully we'll cover different approaches that exists and give you an introduction to it, so that you wouldn't know everything about the method after this discussion, but you would know the names of the methods and the general approaches, what you can get out of it, and hopefully what to Google. That's the idea. And the final thing is, this is a very young field. It's popular. It was popularized in the last 6-7 years, I want to say, and it has been expanding really fast. So there's a very exciting research areas and open questions that remains. And if any one of you is interested in pursuing research in this area, hopefully this discussion today will give you the jumping off point that you need to think about open questions, and what sort of problems do we need to solve in explainable machine learning to make practical impact with that. So we would organize this session into 3 sections. Number 1 would be sort of a presentation where I would try to outline what explainable machine learning is, why we use it, what are the general approaches out there, and stuff like that. And then we'd go to like a more exciting part of hopefully this session. The section 2 would contain some hands-on tools where you could try. We would discuss about three popular tools that are out there, and what demonstrate how you can use them, and I believe you can follow along if you have access to the Colab notebooks. And the third one, we'll come back to sort of a discussion. It'll be great if it's a participatory discussion as well, about some open research questions, and where the field is moving, and where we think the pressing questions are. and what to do next. So we'll quickly look at introduction to machine learning. So we'll discuss these things. What is explainable machine learning? Why is it really important? Why are we discussing this? Why is this such a hot topic these days? How can we use these systems in a practical setting? And what are the existing methods? So these are the things that we would we try to cover in this first half an hour or so. So let's start with what and why. Oh, before we start, can we go quickly poll the audience, if I can get to the audience, to see the experience levels out there, just to get a sense of who's here. Like, are you mostly undergrads? Are you graduate students? Are you in the industry? How can people either unmute yourself and talk, or in the chat, just chat mention. You can just type on the chat like undergrad, industry, or graduate student, or other, if you are. Okay, nothing. All right, I'll assume that most of you are students. So this might be hopefully interesting. So we'll go into the what and the why. So let's take a step back and look at what machine learning is and how we can use it, right? So we use machine learning to help human decisions by doing various things. So thank you very much, a postgraduate student. That's great. Hopefully this will open up some interesting research questions for you. So we do broadly three things, right? We describe data. So that's why we use like clustering techniques and stuff. We detect events and patterns that as they happen. Image recognition, anomaly detection, all of that fall into that category. And we predict or forecast future outcomes using historical data. We estimate how many people are going to come visit our website, or how many people are going to purchase this particular product on this particular sale. If we give this discount, this is how things are going to change. Stuff like that, like predicting future outcomes. And all of those predictions, we generally use that prediction to make some decision. So if we give this discount, how would the sales change? And if the sales are not changing, maybe we shouldn't give the discount, right? So we make small decisions, or very, very crucial decisions about businesses, about public policy, or anything using machine learning models. So how the models that we use these days has come a long way in over the years, right? We can a set of rules, if then rules can be thought of as a model, but it's very, very interpretable. We know exactly what the model is doing. Then we have linear models, where we fit a straight line to a set of data and make predictions. And then we have nonlinear regressions, and so on and so forth. We have ensemble methods now, like random forests, or boosted decision trees, and neural networks and deep neural networks now. So there's the machine learning models are getting more complex by the day. And while we are getting improved accuracy results with these, we have very little understanding what the machine learning model is doing, and how the model is actually coming to these predictions that it's giving us. The only thing that we know is that it's giving us 97% accuracy on a test data set, right? Is that adequate? So this lack of visibility into the machine learning model's decision-making process, we are, as I mentioned, we are limited to this accuracy metrics or the F1 score or plain vanilla accuracy or the false positive rate or anything like that. We're just uh, limited to these numbers on a test metric. These are necessary metrics, by the way. I'm not saying that, but there could be spurious correlations in the data. There could be some data leakage in the model that happens that gives us these good metrics. But these spurious correlations, even though because of the choices that we've made in our modeling pipeline, even though that is giving us good results, that would not realize when we deploy the model in the wild, right? So the question there is, we want to ask, actually, ideally, we would like to ask, is the model doing the right thing for the right reasons? Because it could be doing the right thing for the wrong reasons as well. And the wrong reasons wouldn't generalize to the real world. So deploying these models can lead to very undesirable outcomes. So especially if you are making decisions that can impact someone's life. Imagine, so machine learning models are being used to make decisions about loans, about credit cards, about even in the US, even for making bail decisions, machine learning models are used. Whether someone who has an alleged allegation, should they be granted bail or not. So these are very consequential decisions that are being made using these machine learning models. So it's very imperative that we have some insight into what the machine learning model is learning. So without any surprise, there's a big consensus, general consensus in the community that it is necessary to be able to explain how a machine learning model makes its decisions. So some common themes that we've seen behind this need of explainability in the discourse in media and all of that is lack of human trust. So we don't seem to trust ML models or AI models. Potential biases that could exist in ML models. And now more and more regulatory frameworks are coming up. In GDPR is an example in Europe, where it is, if a decision is made about you using data, there should be an explanation. There's a right to explanation. So just one quick story about this. If you this was a big story a couple of years ago in the US, where Apple released a credit card, and a husband and wife who had the same income, same sort of professional experience, same credit scores, everything applied for the credit card. The husband got like 10 times the credit limit as the wife. And this kept happening. And there was this allegation to the and accusatory tone to Apple, saying that the credit card system is actually sexist. However, Goldman Sachs developed the credit limit algorithm. It was a black box. They didn't know what factors went into the model or what factors were being prioritized by the model. So this was this whole fiasco where it was difficult to audit what the ML model was doing. There was another instance where IBM Watson claimed that they would develop this AI healthcare machine that would help doctors diagnose patients, and doctors didn't use it. They didn't trust the model. It just sat there, and doctors didn't end up using it. So there was a big story around that too. So all of these things put together, it's just screams that we need explainability from machine learning models. Is it that simple though? So what is explainable? How can we what would be an explainable machine learning model? So broadly, so there's no consensus around what exactly the definition is for explainability. And the words interpretability, explainability are being used interchangeably in research. So there's no real well-defined answer there. But broadly defining it, we could say that it's the ability to explain the model and its outputs. So that the decision-making process of the model is sufficiently clear to the user. And what sufficiently clear means is very different from context to context. So let's say it's a machine learning practitioner who developed the model. For them, sufficiently clear is a different thing than the banking official who's actually using that model. So explainability is not a monolithic concept. It's a very context dependent, a use case dependent context. So it's important to identify the fluidity of the nature of it. So, but we could again to make two broad things. Can we understand what the model has learned about the data? This is not simple because the machine learning models very complex, right? So understanding what it has actually learned is a very difficult task. And the second thing is, if given that the machine learning model makes a prediction, can we explain how it got to that specific output? So those are the two main things. I'll be coming back to these two as we go on in the presentation. So it's good to keep that in mind. And the big question is, if we can't explain a complex model, do we have to give up model performance to achieve explainability? Is there a trade-off between the two? How do we perform that balancing act between intelligibility or explainability or interpretability and the actual performance that we care about? So again, we'll take a step back and see how we'll come to that discussion about the trade-off between intelligibility and performance in a few minutes. Let's take a step back and see how we can use explanations in a practice. Let's think about a machine learning pipeline that gets deployed for some decision-making task, right? So at the beginning, you have some problem that we need to solve. You have data related to that. And you have an ML practitioner such as myself, and most of you all in the room would be playing this role as well. So we build some model, we develop some model, machine learning model. We think that it's good enough. But just because it's good enough doesn't just get deployed straight away. There's an approval process that you have to go through in most of the real work. So in that approval process, you have some regulator, some person, high-level decision maker who's making the decision whether to deploy this model in their decision-making process or not, right? And let's say you get the approval. Now you go to the deployment setup where you have deployed the model. Now the model is making predictions and it's in the live system. There are two main ways that the prediction gets used. One is a fully autonomous system where the prediction goes into another algorithm. It makes decisions automatically and there's an action. Think about Netflix recommendations, right? There's no human in the middle there. There's some prediction made about how likely you are to be interested in certain things, and it sorts the TV shows and the movies and the documentaries that the algorithm thinks that you would like and prioritizes them for you, and that's the action. But on the other hand, there are many systems where there's a human in the loop. The machine learning prediction is a piece of information that is given to the human. Human takes that into account and takes some decision, takes some action based on the information that and the domain expertise that they have, right? So there's another human being that interacts with the machine learning model. We call them the action taker. Is that all though? In the end, depending on the action that is taken, there are people, individuals that are getting affected by the action as well. So imagine Facebook. You log in, you have your timeline, and you have posts that are recommended for you that the algorithm thinks that would be interesting for you. If it's actually showing you fake news and other unverified facts, you are affected by that information, right? So and let's think about decision support systems where you make credit lending decisions or like bail decisions got directly affected by the action that was taken based on a machine learning model. So that person indirectly, albeit, interacts with the machine learning model. So the goal of explaining models is to explain it to a human. So now we have 4 types of humans interacting with the machine learning model at different points, right? Let's see how explanations can help them. So let's go back to the beginning. ML practitioner, let's put our developer hat on. What are we trying to do? We're always trying to improve our models and find errors. So the role of the explanation is to help the practitioner or the developer discover errors in the model. The accuracy metrics could be excellent. However, there could be some data leakage issue where you have leaked the information about the output into the input features, and your model is not good enough. Your accuracy metrics would be perfect, but that wouldn't generalize into the world, right? You could have spurious correlations where some data collection process was misguided, or there's some noise in the data that you haven't discovered, or there could be some missing values that you imputed with a certain approach that led to that mistake. Explanations can help you uncover those. Coming back to the regulator, the main decision that they are trying to make is, can I deploy this model? There, the question that the explanations can answer, can I trust this model enough to deploy in the system? So having access to what the model has learned and how the model is making its decisions can be hugely beneficial to that person. Let's go to the action taker. There are 2 main questions that the explanations can help them with. If you take this, so trust, you can see trust here and trust here. Trust, again, is not a monolithic concept, right? There's trust in the model and there's trust in an individual prediction. You can trust a model generally, but not trust an individual prediction. So the action taker has to make a decision there. Okay, does the prediction look good enough? Okay, if there's an explanation behind that, then the action taker can take that into account and say, oh, okay, that makes sense. Then the machine learning prediction must be right. So they can, using the explanations, they can make the decision whether to follow the model's prediction or just override it. And the other side is, let's say you can take 5, you have options of 5 different actions to take. In machine learning models, we just get a prediction, right? We just get a probability or some score that comes out of the model. We don't get instructions on how to act. But if there's an explanation behind that score or prediction, that could act as a guide for us to select the appropriate action. So we call that intervention selection or action selection. ML model explanations can help that. And finally, going to affected individuals, explanations based on decisions can determine whether the action that was taken on them, was it ethical and fair? Is the person getting a lower credit score, getting that lower credit score because they're a woman? So, or is it based on some other reason? Were the reasons reasonable? How? And the other way, if you're denied a loan, can the explanation tell you, if you do these things in the next 2 years, your loan application would be accepted? So guidance into improving their outcomes. So these 5 use cases are, you may have understood that, like, we have very different goals. There are different people interacting with this. So the purpose of explanation is very different. So it's almost natural to expect that one method would not satisfy all of these things, right? So we need to keep these use cases in mind. So I'm not saying that these are the only use cases of explainability, but these 5 buckets can cover the primary use cases. So this is a summary of that. So you have model debugging, you have an end user practitioner explaining what the model has learned, uncovering errors. You have trust for adoption. You have regulators who are making adoption decisions, again explaining what the model has learned and understand how the model makes decisions and potential risks. So this table, I don't know whether we are sharing slides at the end of this, but this table is a good overview of how you could think about explainability in a particular domain, and there can be nuances to this given the domain that you're working in. But if you are ever in a position to define an explainable machine learning method for something, or a machine learning system that has explanations in it, it'll be good to think about like what particular use case are we thinking, who's going to be consuming the explanations, what's the role of the explanation, why are we explaining, what would the person do differently with the explanations, which decision that they're making are we helping with the explanations. So very explicitly think about those things. So that's like what explanation is, explainable ML is, why we need it. A quick time check. I think we are sort of okay. And why we need it, and how we can use explainable ML at different stages of the machine learning pipeline. So what methods are out there? Let's take a quick look at like what are the different methods that exists in the field, and how they map to these particular use cases that we identified. There are two main approaches that exist for explainability, tackling explainability. On one side, you have these complex machine learning models. So I talked about balancing complexity, model performance versus interpretability, right? Explainability. Was there a trade-off there? These two approaches actually is very related there. On the left-hand side, you have, we call them post hoc methods. That means we apply them after the fact, after training the machine learning model. So we don't change the learning algorithm of the model in any way. We train the random forest or the neural network or the boosted trees or any complex model that you want to use as is. And then we have a secondary method that probes that model to extract an explanation, extract what the model has learned, and extract how the model is making individual predictions. And on the other hand, there's the other approach to it. It's saying, no, we shouldn't use black box models at all. Let's develop interpretable models that are simple enough to be interpretable on their own, but we are not compromising the performance. We are actually getting the performance of a very complex model like a neural network or a random forest, but the model is simple enough to be explained. Can it even exist? And there are two levels that we can generate explanations at as well. So one is at the model level. So explaining a model. So we basically explain the general decision-making approach or the decision-making process of the model. So we refer these to as global explanations. It's a very difficult thing to achieve with complex machine learning models, especially like neural networks. It's very difficult to distill it down to a comprehensible set of a comprehensible summary, what it has learned, because it's so complex. And the main methods of achieving this has been like rule-based explanations, like a method like anchors, or through inherently interpretable models where the model itself is the explanation. This hasn't received a lot of attention in the community as of yet. So there's another gap of research that needs attention. The most popular level of explanation has been at individual prediction level. So when the machine learning model makes a prediction, there's a score or a predicted class or whatever. Can we accompany that prediction with an explanation? we refer to this as a local explanation. This type of explanation has received the most attention in the field. So there are different types of methods exist, different types of explanations exist. We'll quickly skim through some of those in a bit. So if we break down these two dimensions, this is how it looks like. So you have the two approaches: inherently explainable models. You have post hoc methods, right? And in the inherently explainable ones, you don't really break down the local versus global, because it's, even though you can extract local and global explanations, it's the method is the model itself. So you don't need to break them down. You have post hoc methods local, and you have post hoc methods global. So in local post hoc methods, the most popular type of explanation has been feature attribution based explanations. That means attributing a feature importance score to each feature for the prediction. And there's example-based explanations. There's something called counterfactuals and contrastive explanations. We'll go through each of these very quickly in a bit. And you have in global explanations, you have rule-based summaries of the model, and you have sometimes where you distill the model into a surrogate model. Like there was this paper by Jeffrey Hinton where he distilled the neural network, the trained neural network, into a decision tree. So now the decision tree behaves like the neural network, but it's interpretable, something like that. We won't spend a ton of time on this section, but we'll spend some time on these two. On this side, inherently explainable models, you have different approaches. You have linear models like linear regression or logistic regression. Those models, you have generalized additive models where you have single feature functions that are added together to generate an unlinear function. You have super sparse linear models that's called SLIM, which is a very popular approach now, where you combine you do a lot of feature pre-processing to get to a level where you can have like just some integer additions and you can get to the prediction. You have rule lists and then you have decision trees. So we'll look at this and this a little bit. So far, are there any questions? Please use the chat or the question and answer thing to ask questions. Okay, no questions. So feature attribution based explanations. So as I mentioned, the goal of this is to assign an importance score to each input feature that quantifies how much they contributed to that particular prediction, right? So in this figure that you can see, the model predicts flu, and the features that went into it were sneeze, weight, headache, no fatigue, and age, right? So the explanation says sneeze contributed towards the prediction, headache contributed towards the prediction, and no fatigue was contributing the other way, a negative contribution. So this is presented to the human, and human puts together sneeze plus headache, maybe adds up to flu. So does that make sense? So this is taken from one of the seminal work called Lyme, this paper by Marco, which kind of was like one of the first feature attribution based methods that came out. So as I mentioned, this is the most popular type of explanations. And there's a bunch of methods that exist, both model specific and model agnostic. Model agnostic means in model agnostic ones, it doesn't matter what the machine learning model is. You can use any machine learning model with these methods. Very two popular approaches are Lyme. locally interpretable model agnostic explanations, and SHAP, which is based on game theoretic Shapley values, where it's a permutation based explanation method, which we will actually demonstrate today and show you how you can use the SHAP package. And in addition, there are model specific ones, which some like tree interpreter, which is specific to boosted trees and bagged trees or random forests. You have tree SHAP again for trees. You have layer-wise relevance propagation or LRP, which is for neural networks, and you have deconvolution type stuff for like convolution neural networks. So these are by no means are these exhaustive lists. These are just examples of what's out there. I'm pretty sure when you start, if you are interested, when you start Googling these things, it'll lead you to the other techniques that are out there. Counterfactuals. It's a very interesting explanation. So in counterfactuals, what we are trying to do is to identify the smallest change in the data that would produce a different outcome from the model. So in a practical sense, think about a credit lending thing. You submit an application for a loan. The machine learning model says, no, you do not qualify. The counterfactual there would be, it would tell you, okay, change this and this and this and reapply, and you get approved. So even in this graphic, this is from the interpretable DICE package. Increase the income by 5,000 and have one more year of credit history. That means maintain a credit card or something for 1 year, make payments on time, and increase your income by $5,000. And when you come back, your loan will be approved. So counterfactual explanations have very big utility in the real world. However, real counterfactuals require you to learn a causal structure of the data or the model, which is not a trivial thing to do. So while the existing counterfactual methods are a step in the right direction, there are big limitations there in the explanations that we can generate. However, the one of the good things is these methods tend to be model agnostic. I say to an extent because if your model is not differentiable, they tend to do like a random search, which is suboptimal in a sense, but you do get an explanation out. If your model is differentiable, then the optimization function that they're actually solving for, it can be solved. So like a neural network would actually be beneficial. And there's several methods out there that is popular. One of which we'll discuss today, called DICE. It's diverse counterfactual explanations. That's what DICE is. FACE is feasible and actionable counterfactual explanations, because just because you, so that's an important one, because let the model says decrease your age by 10 years and you'd get your loan. It's not actionable or feasible, right? So you need to find a perturbation in the data that is actually doable and changeable. So that's what the algorithm FACE is dealing with. MACE is one of the first ones that came out, if I'm not mistaken. It's model agnostic counterfactual explanations. And the last one is foil trees, which is a very interesting one. It generates something called a contrastive explanation, which is almost a counterfactual, but it's kind of different in a way. It explains, so if you have two classes, class A and class B, when a model says this prediction belongs to class A, the explanation says this particular instance was assigned to class A because the feature was 20, not 35. This feature was 40, not 75. Like, it gives a contrastive. So So had this been 75, it would have been class B. So it is a counterfactual in a way, but they call it a contrastive explanation. It's an interesting method too. But again, there are some practical limitations in that we tried to use those methods in a practical setting, but it was very difficult to get them to work. We don't have time to get into all those details, but good to read about these things. Example-based explanations, and here the instance is explained by using examples from data. So instances from data are used to explain another instance. So for instance, if you look at this graph, so it's a set of prototypes. So we call those instances prototypes. So prototypes generated for MNIST, it's by a method called MMD critic, where all these zeros are prototypes of zeros. So if a data point comes that looks like this, the model would say, okay, it's a zero because it looks like this particular one. So that's the explanation. A similar instance is an explanation. So that can be helpful in like images, but might be tricky with tabular data because it's difficult to present tabular data in a human understandable way. But there could be some modifications to that. There are a couple of algorithms that are out there, not heavily studied this field again. MMD critic is one of the most popular ones. Would be good to read about that. They talk about prototypes and something called a criticism as well. So criticism is something that doesn't conform to the prototype that you select. It's an interesting read. And there's another algorithm called protodash where you actually find the prototypes that like this. And nearest neighbor algorithm can be thought of as an interpretable model that generates explanations of examples, because you basically find the nearest neighbor, and the nearest neighbor's label is assigned to you, and the explanation of the prediction is the nearest neighbor, so which is an example. So it can be thought of an example-based explanation. And counterfactuals, adversarial examples, if you may have heard about adversarial learning, and are also thought of as example-based explanations because we are not giving a feature-based explanation, but another instance as an explanation. Inherently explainable models. So there's a big case for that because Cynthia Rudin, who's from Duke, Rich Caruana, who's at Microsoft Research, are two of very vocal proponents of this approach for explainable machine learning. If you're interested in this field, I encourage you to go and read their work because they do really interesting stuff. The case is with the post-hoc explainer, you are actually approximating how the model would behave. So there's no ground truth that you can check it with. So there's no theoretical guarantees of faithfulness or anything like that. So in a high stake setting, that approximation, if it's not correct, could lead to disastrous outcomes. So the argument is simple models can be made accurate enough, so we don't need to use complex models. So work on the simple models, make them more accurate, and use them in high stakes decisions rather than using black box models and trying to explain them using post hoc methods. So a couple of popular work in there is something called SLIM, or super sparse linear integer models, and generalized additive models. These methods in the context of the papers and their studies have shown to be as accurate as a complex model like a random forest, but is there a guarantee that this would generalize to all contexts? We don't know. So that there's something that we need to evaluate. In the case of SLIM, it relies on very careful preparation of features. So you need to do a very careful selection of features, and you need to binarize features. So there's a lot of implicit choices that the machine learning engineer makes, which that is not explained anywhere. So even though you get this shrunk down feature space and very simple model, how you got there is not explainable. There's this butting of heads in the principles there. And the other thing is this binarization and feature engineering can be prohibitive in a very large feature space, because in one of the projects that our group has done, it's putting together healthcare records, mental health history, incarceration history of people. So there's like 5 different data sources coming in, linked together, creating this humongous feature space with thousands and thousands of features. How do you go from there to a distilled 20 feature space where you have binary features identified? So it can be prohibitive in very large feature spaces, but a very interesting idea nonetheless, and requires more testing. Generalized additive models are very interesting ideas. So in the plain version of GAMS, it's just an addition of a bunch of single variable functions. So in this GAM2s, they basically included pairwise interaction features to that. So it's a very cool approach of thinking about interpretable the models, because you have single feature functions and you have 2 feature functions. You can visualize single feature functions by just one line plot, and 2 feature functions by a heat map. So you can visualize how each component contributes to the score, which is an explanation, and that's very cool. And we'll be showing this the method today in our demo session. It's the implementation of this is called EBMs, or explainable boosting machine. And how do they actually connect to our use cases? If you take model debugging, you need to understand errors in the model. So local explanations and global explanations both would help. Trust and model adoption. Here we need to explain to a regulator how the model generally makes decisions. So mostly global explanations are helpful. In the two cases where we present explanations to the action taker, they're taking decisions about an individual instance or individual person. So local explanations are more helpful. And recourse to local explanations are helpful because they're making decisions about an individual prediction. How to change the individual prediction, especially counterfactuals can be useful in that use case. Evaluation of interpretability, we'll come back to this in section 3. Before we go there, we'll break here for a bit and answer any questions that you may have. There's no questions posted. Is it because it's so boring, or is it, have you understood everything or understood nothing? Or I would like to hear from you a little bit. No one's listening. Okay, cool. Doesn't look like there's any questions. We'll move on to the second session, which is a hands-on session. Dr. Damayanti, I'll pass it on to you.
Yeah, thank you, Kasun. I hope you can see me and hear me. Yeah, so good morning, everyone, and thank you for joining this session and showing your interest on this particular topic. So let me share my screen. Right. Oh, so, okay. So we at Peradeniya University at the Department of Computer Engineering with the machine learning group, we have been looking at different machine learning methods, models, as well as different learning algorithms And of course, there are applications in various domains, like in education, biology, likewise. And what we have observed is that there's a huge potential and space for improvement in terms of understanding these models, so which concerns with explainability in machine learning. And that was our motivation to organize this particular tutorial today. And I believe it is like, it's kind of first of its kind that we are discussing it at an international conference that is happening in Sri Lanka with a community like this. So that's great. It's great to have you all at the session today. And so from here onwards, we are going to discuss or present a couple of tools or methods that are available for explainable machine learning. And particularly, we are going to focus on SHAP, DICE, and EBM. And actually, our intuition here is not to promote any of these methods, but rather to give you a flavor of what is existing and what sort of work has been done. And of course, there's still space for improvement, as Dr. Kasun will discuss later. So if you are interested, you can hear our contact details if you are interested or if you will be pursuing this topic further. So with that, I'll move on to what I'm going to talk about in this particular tutorial. And if you want to access the slides or the code that we are going to share in this tutorial, I have given the link in the chat. And so you can access that instruction sheet. And there we have given the necessary links for these slides and the code. And also, yeah, and I have also shared a link for a feedback form. So when we talk about SHAP, it is a method that's been, in fact, I think was initiated and now it's still being developed with getting more features added for explainable machine learning. And if you think about the categorization of this method, what it can do, it's a model agnostic interpretation model. So the idea is you can develop an explainable method. You can develop an explainable model that is specific to a certain model, right? For example, we can consider only the tree-based methods, tree-based models, like decision tree-based models or random forest, something like that. But the disadvantage is that we are limited to a certain model type. But as with something like SHAP, the idea is it's model agnostic, meaning that it can be applied on any type of machine learning model. But of course, there are some variations of implementation, SHAP implementation, that is specific for certain models. So we'll look at them as well. And this is a local interpretation method. As Dr. Kasun mentioned, we can categorize explanations as local explanations and global explanations. The idea in local interpretation is that we try to explain individual prediction. Whereas in global interpretation, our objective is to understand the overall decision-making process of the model as a whole. But SHAP was designed as a local interpretation method, but it can be used for global interpretation as well, but it was mainly proposed as a local interpretation method, meaning that to explain individual prediction. And if you look at the foundation of SHAP tool, Shapley additive explanations, it is based on the Shapley values. So I have a little figure as an example here. It's taken from this Interpretable ML book. And so this example, what it says is, let us assume that we have particular regression task where we want to predict the price of a building. So what this says is that, so if for a particular instance where there's a park nearby and there's a floor size of 50 square meters and with like 2 floors and the cats are banned, the price has been 300,000. So the idea in Shapley values is that we consider now in local interpretation, what we want to know is when we get a prediction like 300,000, how much each of this feature contributed for that prediction. So what in Shapley, what we do is it's based on a game theoretic approach where we consider that each feature value is like a player in a game, and this predicted value is our payout. And we try to divide the payout among these players, meaning our features, so that we can match to the average. For example, let's say our average prediction for this particular data set, in average, the prediction has to be 310,000. But what we have predicted is 300,000. So we see there's a 10,000 gap. So now what we can do is we can see at each feature, and we try to see how much this feature contributed for that particular gap. And by that, we try to quantify their contribution for that particular prediction. And I'm not going to go into the details of the implementation, but that is the kind of the intuition behind Shapley values. And the tool SHAP is based on Shapley values. And it is an attribution method. Dr. Kasun briefly mentioned about this also. That is that what that means is that a single instance, like a single prediction like this, is described as the sum of, it's a sum of all the feature effects. Right. So in fact, we are doing a 2-hour tutorial on this particular topic, and there are a lot of things we can in fact talk only about SHAP. But there's a very comprehensive tutorial which I wanted to share with the attendees today on SHAP from SHAP itself. And so I have given the link here, and also, give me a second. Also, as we looked at, it's implemented to explain the output of any machine learning model. For example, maybe like a k-nearest neighbor classifier or linear regression model, or maybe something quite complex as a random forest or its variant. So, and also it has some extensions that are model specific as well. For example, they have provided with an implementation that is specifically catered for tree-based models. So I would say go to for any, if you want to look at different implementations and their applications of SHAP, I think a go-to would be this GitHub link, and they have provided a very comprehensive. If we quickly go there, they provide a comprehensive details about what are the different variants of SHAP that we can have. For example, they're showing how it can be applied for an image data set, maybe, and also some tabular data, etc. So this is, I think, very good documentation there, and you can try out these different examples. So going back to the slideshow, so today we are going to focus on 3 tools, SHAP, DICE, and EBM, and we are going to consider this particular adult census data from UCI. If you are new to machine learning, for the benefit of them, I just mentioned what UCI is. So UCI is a repository of data sets, mainly with the tabular data sets, and that's a very useful data set if you are beginning with machine learning, because it contains a lot of data sets that you can experiment, that you can use to experiment different machine learning methods. So it's a very valuable source, UCI repository. So this particular adult census data set comes from the UCI repository, and these are the characteristics of that data set. So it's a multivariate data set with this number of, considerably large number of instances, and we have 14 attributes, or the 14 features. And now the question to ask is, now I have presented what's the data set, and now the next question is, what are we going to do with data set? So the particular problem in this for this data set, or what we are considering here, is to determine whether a person makes over 50K a year. So if a person makes over 50K a year, we make it, the label would be 1, otherwise it's 0. So as you can understand, it's a labeled, we have labeled data. So it's a supervised learning problem. And because we are trying to predict a label, or we are trying to do a classification, this is a classification problem. So, and this, it is specified in the instruction sheet as well. I have shared the Google Colab notebook in that here. And before, if I can, maybe if I can ask quickly, how many of you are already familiar with the Google Colab tool? Can you raise hand? Yeah, it's great that we see that some hands are going up. And let me make this an opportunity to introduce this tool as well, the Google Collaboratory, which we call in as Colab, Google Colab in short. It allows us to write and execute Python in our browser, which is quite convenient. With so this is the Colab homepage. So it allows us to run that with zero configuration on our system, and it gives us the good thing is it gives us free access to GPUs, and it's easy to share as we have done now. So I hope that this tutorial also inspires you to use this tool, Google Colab. So let me go to my Colab notebook where I try to demonstrate the use of SHAP. So you can install just as similar to any Python package, we can install SHAP using pip install. And after that, I am importing the necessary packages, including SHAP. And before going further, we'll try to explore the data. And so if you try to list how the data set looks like, this is how it would look like. And these are the column, these are the feature names that we are having here. We have features like age, work class, marital status, relationship, etc. And now, before doing anything in a machine learning project, the first thing would be to split your data into train and test, or whatever the data split that you have chosen for your evaluation, maybe train, test, validation, or likewise. So here we are only dividing it as a train test, as a simple split. And then this example shows training a bit complex model, the light gradient boosting machine model, which is based on, it's a tree-based model. And then we can generate an explainer using SHAP. And for now, because I'll let you play around with this in your own time, but I'll take this time to go through together what exactly we can do with this. So, and what is the output, or what we are seeing here. So, and another thing I want to mention is it appears that we had to call this shap.init.js at every time in the code snippet when we want to visualize the outputs. And I think it is missing in the documentation, so I thought it's good to mention it here. So what we are seeing here is the feature value, the features, how much their payouts, in fact, for a particular prediction. In fact, here the very first prediction. So the base value, what it says is that is the average that we want to have. And here, but what we have got is something like minus 8.43. And what this says is the red corresponds to the increase and the blue corresponds to a decrease. What it says is that the features like age, sex, education, they have increased this prediction. and by these amounts, and capital gain relationships, they have contributed to decrease that, or in comparison to the average that we wanted to have. So we can do this kind of analysis for each of the prediction and see how was the contribution from each feature to that for that particular prediction. And in addition to that, we can do a summary plot, kind of an implication of the feature importance, not exactly like what we do with random forest, but I mean, the method is different. But again, we can get an understanding about the feature importance, but looking at the whole data set. If you look at the whole set of predictions, we can plot a summary plot of Shapley values or the Shapley values. So what this basically says is, if you sort the features by the Shapley values, we see that relationship contributes most for all the predictions for both the classes. And something like marital status, it has low contribution for a prediction, like the class 0 or class 1. And in addition to that, we can do dependence. We can do things like dependence plots, which considers, in fact, the interaction between features as well. So as I mentioned, there's a very good documentation on SHAP. So, and also you can take this as like a starting point and explore further on SHAP. And yeah, there was a question asked that whether Google Colab supports Java. And as far as I know, it does not. I think it is for supported. It is for mainly for Python programming. And also there's another alternative tool we could have used alternative to Google Colab, that is Binder. And yeah, so that there you can have a Docker instance and you can run your codes. So that is like an alternative for Google Colab, Binder. So I think almost that is all I had to share. And with that, I'll hand it over to Amila to discuss about DICE.
Hello, I hope everyone can hear me. So let me share my screen. I hope you all can see this. So DICE is like a counterfactual explanation method. So it's called diverse counterfactual explanation. So it's named DICE. So this is an overview of DICE. So as Dr. Kasun explained, in counterfactuals, what we are like interested in is what should be changed in order to change the output. In usual machine learning models, what we try to do is like we are interested in the output for a given input. But in counterfactuals, we are interested in the reverse question. So what change should be done to the input data so that the model predicts another like different output. So consider this example. There's an applicant who's applying for a loan. So it was for some reason rejected by the machine learning model that we are using. So the interesting question is like what should the applicant improve in order to get the loan approved the next time. So for that we could use this like DICE tool to generate such counterfactuals. And as of now, DICE support these kind of methods like sklearn, TensorFlow, and PyTorch. So I'll like dive into the details of like how we can use sklearn in the demonstration. So consider this like this figure to get an idea about the counterfactuals. So here consider this loan application thing. So originally the original decision of the ML model is like, so is that the loan is rejected. So by increasing the income by this amount, we are saying that the loan can be approved. So that's a counterfactual. So consider this case, like as Dr. Kasun explained. So original prediction was the loan was rejected. So by increasing the income by this amount and having a 1 more year of credit history, the output can be changed. So that's what counterfactuals mean. So we can use this DICE tool to generate such counterfactuals. So this is an example with the data set we showed earlier. So this is the same data set, that adult income data set. So here consider this instance. So these are the input features in this instance. So these are the input features, and what we are trying to predict is this income feature, whether it's greater than 50,000 or less than 50,000. So if it's like less than or equal 50,000, it's labeled as 0. If it is greater than 50,000, we label it as 1. So as you can see here, so this is the input instance, and for the output instance, we have generated 2 counterfactuals. So here, as you can see, we are saying that this in the input data set, the education is high school graduate. So we are saying that by changing the education to a master's and changing the occupation to sales, he can increase the income. So that's a counterfactual. And in this other counterfactual, we are saying that he's currently working in the private sector. By changing his working class into the government sector and changing the education to associate, he can increase his income. So that's another counterfactual. So I hope everyone understood what counterfactual means and the idea behind counterfactuals. So there are some advantages and like disadvantages associated with DICE. So when we talk about the advantages for end users, like they provide like actionable alternatives, like what could be improved in order to change the outcome. So when they are applying or like applying for the next time. So for machine learning developers, it might be helpful for debugging purposes, and for decision makers, it helps them to like trust the machine learning model predictions. And in terms of the disadvantages, there are certain limitations with DICE. As of now, like it, as I showed you earlier, it only provides you a tabular output, and like there's no explanation in English, like as I showed you here. So it's just a tabular output, like there's no explanation in English. Like you have to look at this tabular output and understand what this means. So this is like currently developing by the developers. So that's a limitation in DICE. And as Dr. Kasun explained earlier, like there are some like feasibility issues associated with DICE. Like in fact, like the counterfactual may ask you to change the age from 22 to 20, which is not possible. So that is a limitation with this DICE. So another limitation is that like it only supports certain kind of optimizations, and some of the optimizations are currently not supported. So that's a quick overview of the dice. So I have added some references so that you can refer. So we'll then move on to the demonstration. Hope you all can see this. So first, I'm importing the SK line. Like for this demonstration, I'll just go with the SK line model, and you can refer to the documentation to see how you can use TensorFlow and other PyTorch models. So for this demonstration, I'll be using this SKLAN model. So in fact, we'll be using this random forest classifier. And first, we are just importing the SKLAN models and required libraries. And then you can directly install with a simple pip install, and then install the dice, and you can import the dice library and the required helper functions. And so then we are in the next stage, we are loading the data set and we are training a ML model over the data set. So there, first we have to load the data set. Here there are some pre-processing associated with the data set, and it is supported already given by this machine learning the dice ML model. So you can go through this link and refer to that. So if you look here, these are just some pre-processing done to the raw data set. So you can go through that, just some variable changing and some pre-processing. You can refer to that. So after loading the data set, this would be the input data set. So then you can have a quick overview of the data set, a quick description here. And then we are doing some train test split to separate the data set. And I hope most of you are familiar with the train test split and everything. So we are just splitting it into 80-20. Then we consider about the loading a machine learning model and training a machine learning model. So here as you can see in this data set, this age feature and the hours per week, these are numerical features. So we are saying here that these features are numerical and other features are categorical. So then as you might know, we have to transform these categorical variables using some sort of encoder. So here we are using this one-hot encoder, and then we are training the random forest classifier. I hope it's clear to everyone up to this point. So after training the model, you can create a dice instance. So in the dice model, first you can specify the metadata that we are providing for the dice model. So using this dice ML, the data function, you are just providing the trained data set, and we are specifying the numeric features since there are categorical and numerical features, we have to specify what are the numerical features to this dice model, and we are saying the target variable here, the what we are trying to predict. So that's income. So that's the metadata about the data set. Then here we are creating a dice instance here. So we are like here we train the machine learning model and save it in this model variable, and then we have to provide the train model to this dice instance. So that's what we are doing here. And for the backend, as I explained earlier, we are using the scalar. And if you refer to this link, you can see how you can use TensorFlow and PyTorch and provide that as the backend. For the demonstration purposes, we will use only a scalar and here. And after like training the dice model, we can like create an explainer. So here we have to like provide this like created dice model and the metadata, this dice data as the inputs. And here this method is another parameter in this explainer. So if you refer to this link, so if you refer to this link, so there are like two approaches, like model agnostic methods and gradient based methods. So I'm not like going to go into deep regarding this. So in roughly speaking, this model agnostic means basically for scalar models, and the other gradient based methods are mainly used for neural networks and other TensorFlow and PyTorch models. So that's the rough idea. And you can read more about these individual methods, this random sampling and other approaches. And after we like created the explainer, then we can generate the counterfactuals using this generate counterfactuals method. So here we have to first like provide the input instance, and using this parameter, this total counterfactuals, we are specifying that we need 2 counterfactuals generated. And by this, like the desired class equals opposite means like what is the counterfactual that generates the opposite class. So here there are only like two classes, 0 and 1. So in order to change from 0 to 1, generate a counterfactual. So that's what this desired class equal opposite means. So in case of a multi-class classification, like we can directly specify the class here. And after like generating the explanation, we can like visualize the changes. Like when we are setting this show only the changes equal to true, we are saying like show the changes that we need to make. So if you look here, so this is the input instance, and the initial income value is, the target value is 0. So these are the 2 counterfactuals that is generated. So here the work class is private and the occupation is blue collar. So one counterfactual is that the work class should be changed to government and the occupation should be changed to professional. So if that happens, the income will be greater than 50,000. And as you can see, so this is like one limitation that I mentioned earlier. So it can like generate like counterfactuals which are not feasible. If you see here, like age is 29, like, but the counterfactual says to change the age to 20. So that's not possible. So like that's a like a limitation as of now, and like we have to be cautious about such limitations. And in addition, like we can specify the like specific features to vary. So if you look here, so we can specify which specific features to vary and which features to keep constant. So here, if you see this output, we are only changing this work class feature and education feature. So by only changing these features, what are the counterfactuals? So that's what this like features to vary parameter means. And if you look further down in this permitted range parameter, we can even specify the permitted range for the feature. So here we are specifying that age should be between 20 to 30, and the education should be either doctorate or a professor at school. So these are some like parameters that you can like change and see, so that like you can refine the search space. So that's a like quick demonstration of the dice. So if you guys have any questions, I can answer. So there's a question like, since we can't change the age variable, can we exclude it and check whether, yeah, like using this features to vary parameter, yeah, here. If you look here, you can specify the features that you need to vary, you can vary. So by specifying the several features, we can exclude age and like get the counterfactuals. Any more questions? So if there are no questions, I hope we can move on to the next demonstration. Shaman will continue the rest.
Hello everyone. Hope you can see me and see my slides. So I'm going to introduce you about the explainable boosting machines or EBM. And Dr. Kasun already introduced you about this one, a little bit about this one. So I'm going to explain somewhat deep into the EBMs. So some of you may already have hear about this one. So there is a trade-off between the accuracy and the intelligibility of the models. So for like the methods like machine learning methods like neural nets and random forest, there seems to be having high accuracy, but at the same time their explainability or the intelligibility is somewhat less. So in the other hand, the methods like logistic regression and naive Bayes so are like them are somewhat more intelligible, but the accuracy they are somewhat less. But a research team from Microsoft, including the Rich Caruana, they have made a method called EBM or explainable boosting machine. So it's claimed to have both accuracy and the intelligibility. And so EBM is a glass box model. So basically, its explanations are specific to the model, and it's already inherently explainable. And they are claiming that the accuracy is going to going to have same with the state of the art method like random forest and boosted trees. You know, those two of them are black box models. And it's a improved version of generalized additive model. So some of you might know about generalized additive model or GAM. So it's like so it's more like linear combination of functions due with the beta or the intercepts. So each function is going to make decisions on each variable. For like if you take the age and the education variable from the previous dataset, which was used by Amila and Dr. Damayanti. So it's going to make decisions on age, and then this one is going to make decisions on education variable. So finally they are going to be added together and make the final prediction. So in the EBM, so what they have done is they have make some improvements. So they actually it's called as GA2Ms. The two means they are going to take pairwise interactions of the variables. Here we only had the variables with single interactions. That means only a single variable is going to train on one function. But here they are going to make pairwise interactions, and in EBM they are going to automatically detect the best interactions for the model. And in terms of the explainability, so the EBM have both global and local explanations. The global explanations are solely made on the training data set. So it's going to explain what is happening there in the model. And the local explanations there, it is going to make explanations on the testing data. So I'm going to describe a bit more about how this EBM works. So here, simple decision trees are going to be trained on each features. For like, it's going to start here, train a simple tree on the feature one. For like, it might be age variable. So then it's going to take its residual and going to train another tree solely on the feature two, and this is going to continue. And again, it's going to be iterate on many iterations. And you know, this is called boosting and bagging. So finally, the model is going to make shape functions. Those shape functions are accumulations of these trees by boosting and bagging. So the EBM is going to dump these trees, and it's going to have these shape functions for its decisions. As you can see, so we know what's going to happen there with each variable. So we have a shape function, and these the scores from these functions will be added together when making decisions. So this is the kind of global explanations given by EBM. So it gives how the each variable has contributed to the learning of the machine learning model. These are mean absolute scores, like the dataset which you use last, the marital status, it has contributed the most. Likewise, as I said before, so pairwise interactions are also going to take into consideration, like age into education. So I'll describe more in the demonstration. So this is the look when it comes to local explanations. So it's going to say what has happened there when making the predictions, and how the predictions have been predicted on the shape functions and the scores from those shape functions. I think we can move on to the demonstration. So if you have any questions from the slides, you can direct them in the chat. Okay, let's move on to the demonstration. So first we are going to import the required packages. So the EBM is implemented on the interpret ML package. So it has been developed by Microsoft Research, and the same one which was developed the DICE, I think. So we are importing here the required packages like pandas and numpy, and also for training and test splitting we are using a scalar. And this is how we are going to import this glassbox model explainable boosting machine classifier. And these are some helper functions for study. So I'm not going to describe about the data set. So it was already described by Dr. Damayanti and Amila. So here I like to highlight that we have converted the class labels into 0 and 1. Actually, this was done for the sake of the calculating the ROC curve, so it can't handle string labels. But I should mention that the EBM can handle the string variables and also the categorical variables in the data set. So it is like this, the data set. So then we are going to test the split the train and the test data set. So we are going to take 20% as the testing data set. And here's how we are going to initiate the explainable boosting classifier. And here only I have given two inputs, I mean the options. So the random state, seed, we are setting seed to have the same results when running again and again. So to enable the parallelism, the end jobs is given to -1. So if you go through the documentation of the EBM package, you can see the other options you can give into the explainable boosting machines. This is the documentation of EBM, but it's not that much comprehensible, but it serves the purpose. So you can refer into it. And then we are going to feed the model, and then let's move on to the global explanation. So this is how we are going to take global explanations. Global explanations means we are going to get the description about how the model has, what the model has learned, and what the models are going to be predicted. And it's like overall understanding about the each feature and how it's going to contribute for the prediction. So I'll first move on to each shape function. So as I said before, these are the shape functions for, like, this is for the age. The IBM has learned this shape function as in its classifier. So these are the densities. That means in the training data set, this is how the trading instances has been distributed over the data set. So this is going to this age. This is actually a continuous. That means a numerical variable. So this is how the feature function is for the age. So let's think that there is an instance with age between 51.1 and 55.9. So it's going to give a score of 0.79 to the contribution to the prediction. Likewise, so in the categorical one also, so for like if the work class is private, then it's going to be contributed this much of amount to the final prediction, like 0.081. And from these shape functions is going to make a summary. So I'm not going to describe how these values are generated. So it's more like the contribution from each variable. Then let's move on to the local explanations. So here we can explain instances from our test data set. Let's take instance like this one. So this describes how much each variable has contributed to each prediction. So this is the predicted class, and this is the actual class, and this is the probability of having that class. That means since it is a binary one, so it's I think it's over than 0.5 probability, it's taken as 0. So here's the intercept. Intercept is common to all the predictions. I mean, it's generalized to the trained model. So this is going to be added in the each prediction, and the values like for like this one, the relationship has contributed the most, like minus 0.59. So this value has come from here. So if we go to the relationship variable, let me check this one. This is the shape function. So here the relationship is unmarried. So let's take this one, the unmarried. It has a contribution score of minus 0.591. So it's going to be here. Likewise, it's going to take all the corresponding contribution scores from the shape functions. So for like, yeah, I forgot to mention that the pairwise interaction terms for like this one. Let's say this. So this is the specialty of GA2M or the EBM. So they make use of the interaction terms. So for like here, so if let's take the education num is 10 and the web class is local government, so it's going to be contributed negative 0.019 to the final prediction. So here's the scale bar which shows the values correspond to this heat map. So those values are also going to be taken in the local predictions also. This is such a one, and this is going to be added together. Basically, these shape functions are made on the logarithmic scale or the logarithmic scale, because in the probability domain, so we can't add probabilities together. So these functions have been trained on the logarithmic scale, so these values can be added together. So finally, when making predictions, these values are going to be added together, and that value will be passed to a softmax function or sigma. So it's going to be converted back to the probability domain. So that's the value here. So that's how this is making predictions. And I am also going to show the incorrectly predicted instance here. So by looking at this graph, so you can get an understanding of what has gone wrong. I mean, how the contributions has made for the final predictions, and so what has been contributed the most, and so we can get an understanding what has gone wrong. And so as the EVM is claiming to have comparable accuracy with the models like random forest, I'm going to train a random forest model, and this is how we are going to train. As you know, the random forest model in sklearn can't handle categorical values, so we have to turn them into the one hot encoding, and with both together with the categorical value, one hot encoding values and numerical values, we are going to train a random forest model, and we are going to use the same seed, so you don't have to worry about the splitting of the instances. So it's going to be the same as with the EBM, and we are going to make the ROC curve. So as you can see, random forest has scored 0.9087, and when we are going to for the EBM, so we have got area under the curve of 0.911. So as you can see, they both are having some same the accuracy. I mean, in the ROC curve wise, actually we can put this graph both together, but in the as this is Colab is a cloud environment, we can't do that, so it's not tenable. As last, as a summary, I would like to emphasize the advantage of this EBM. So as you know, it's a well-performed machine learning method in accuracy wise, and also in some other metrics also. Also, it's having the inheritable explainable characteristic. At the same time, it is a open source one, so even you can contribute for it and you can use those codes for your projects and research. But there are some limitations on it, especially the multi-class classification is still experimental, so it has been done yet. So actually here we have used EBM for binary classification, so you can use it for the regression also. In the accuracy, if you need a model like that, but you might have sophisticated machine learning method like neural networks, which might surpass EBM. So actually, this is an interesting area. So you can apply this into many domains. So even me and Amila, we both are from computer engineering department. So we graduated and we were also working on such problem like applications of the CBM on the educational domain, where we are inspecting how the performance will be made. I mean the performance of the students and what are the factors that affecting for it. So it's such a beautiful area. So you also might see that there are a lot of students from universities also, and from also from the University of Peradeniya, you might also join such kind of research. And this is still a immature area, so there are a lot of research gaps. And I think Dr. Kasun is going to describe more about the research gaps and the opportunities in this area. So if there are no questions, I can hand over to him.
Thank you so much, Shaman, and thank you to Amila and Dr. Amity as well. That was all three great presentations. I hope everybody present here today has a better understanding of how to use these methods now, because it's nothing as good as actually seeing and trying it out for yourself. So please make use of the Colab notebooks that are out there to test these methods on different problems, not just on, of course, repeat the things on adult data set to see, but as Shaman mentioned, please make use of the other data sets that are available for free, and just try them out and play around with them to make sure you understand what these methods do. As we are almost at the 2-hour mark, and it's kind of midnight. Yeah, I'll quickly go through a couple of open research areas that are in this space, and we can always continue the discussions over email and stuff after as well. So quickly, I'll share my screen. So I stopped earlier about talking about evaluation of interpretability, which is like the biggest open area, because it's not entirely clear what it means to be interpretable, or what is a good explanation, and it's a context-driven thing, right? Like from the examples that that were shown to you before, a good explanation there might be different from a different context, like education context that Shaman talked about. There might be a different good explanation, a definition of a good explanation. And how do we compare two methods? So if you were paying close attention to those three methods, you might have seen that age, relationship, marital status all seem to come up regardless of so this was not the same explanation, same machine learning model that was explained, right? So each of them trained their own machine learning model and used a different method to explain it. And it seems like the machine learning model are focusing on very common factors. So there's some inherent thing about those features that is helping the machine learning model to discriminate between the two classes there. So, but how do we know what's the best method out there? Like, is DICE better than SHAP? Is EBM better? So EBM and random forest got very similar accuracy metric. So is random forest with SHAP better than EBM, or is EBM better? So how do we compare? What are the metrics that we can use to compare? So these things are not entirely clear or well defined yet. Okay, so computer is yeah. So there are multiple dimensions of evaluating explanations. The first thing that we need to look at is the explanation correct? As in, is it actually explaining the prediction, that is it actually faithful to the model that it's explaining? So if it's not even doing that, then we are being misled by the explanation, right? So that's number one. Number two, is the explanation robust? That means if we run the the explanation algorithm 100 times, will it give me the same explanation all 100 times, or is it different? And if it's different, how do I know? Is it running it 100 times and taking the mean, or is there a variance metric that I need to be aware of? And the third one, is the explanation actually useful to the person who's making the decisions based on that explanation? So it can be, the explanation can be perfectly faithful, it can be perfectly robust, but if it's not helping the human being do a better job at what they're doing, then it's useless, right? So why did we develop all of these methods if it's not actually helping a user do something differently, or make better decisions in the real world? Unfortunately, most of the work that has happened in this field has been focusing on the first two questions, or questions related to that: robustness, faithfulness, or fidelity. Those are the things that we have been evaluating in explanations, not necessarily the usefulness side. Even when we have evaluated the usefulness side of algorithms, we've tend to like use benchmark problems, or users from Amazon Mechanical Turk or something like that, that is not representative of the real world setting. So those evaluations don't really give us an idea of how these methods perform in a real world setting. So there's a huge gap in understanding how these methods are, even though they're actually cool, to see like they give us insights on like a constrained setting like adult data. Are they actually useful in a complex real world setting? So in that light, so the answer to that is we don't know. So we have no idea whether SHAP is useful in helping a person decide whether a person should someone should get a loan or not. We don't know. It's not tested. We have no idea. So while these methods are really clever and really nice, really great steps in the right direction, we are still not clear how impactful they are in a practical setting. So that is a huge gap that we need to fill. So one reason for this is the fact how we have approached the field of explainability. So we've gone ahead. So we are understood as a community that we need explainability. Okay, we need to make algorithms explainable. But we didn't really stop to think why we need explainability and who would use it for what purpose. We just went ahead and started developing methods as we do, right? So, but a goal for developing the method is a very generic, vague one. What do we want to do? We want to make things transparent. But why? I don't know. For whom? I don't know. So while we have these really cool techniques to extract a set of importance scores, a counterfactual, or a method that gives us coefficients for how important each piece of the puzzle is, we don't know what goal that explanation serves. So it is very difficult to quantify whether we actually meet that goal, right? When we don't have a specific measurable goal, we don't know whether we meet it or not. How do we know if the goal is transparency? How do we quantify transparency? So is it, yeah, so how would we define that? So there's a huge gap there in understanding what are the specific goals that we are addressing. The second one, it's actually a corollary of the first gap. The existing methods are not sufficiently evaluated on the impact on human decisions. Because our goals haven't been explicit enough, of course, we haven't evaluated them on those use cases. We have been testing things out on benchmark data sets like MNIST or simple image classification stuff, or adult data, or like news groups and all these UCI benchmark data sets, which are important as first steps. However, we haven't gone that further step to understand how these things actually help human beings make better decisions. So, as I mentioned, efficacy or effectiveness of these methods in the real world remains unclear. So we need to do a better job of understanding how these things perform in the real world. For machine learning models, we have well-defined metrics, right? We have the F1 score. For different cases, we would have precision, we would optimize for recall, we would optimize for minimizing the false positive rate. Like all of that thing, those things are well defined. We know how to attach a number to this thing and compare two things side by side and say, and this is better. We need to come up with ways to do that for explanation methods, so which we don't have yet. So how can we address these gaps? The first thing is we have to figure out how to evaluate these existing methods on different use cases. So I mentioned 5 different use cases before, right? Can we actually conduct experiments to evaluate existing methods to give us a score of how good SHAP is at helping a machine learning practitioner identify bugs in the model, or how good SHAP is at helping a regulator develop trust in the model so that they could deploy. So the only way to do that is to run trials with real users in real problems with real data. So that those 3 things, if you are taking anything away about evaluating explanations, 3 things: real problems, real data, real users. So we need those things to come together, and we need to run user trials that are carefully designed to isolate the impact of explanations and see whether that explanation actually helps people do better things. We need to start developing methods for targeted use cases, not just generic use cases. We need to start from the requirements of a use case and develop methods to that, not develop a general method and try to retrofit it into a use case. So that approach is kind of missing. It would be great for us to evaluate how we can do that. Maybe it's some use case of understanding the indicators of education outcomes, as Shaman mentioned before, something like that. So how do we develop an explainable method that is addressing the needs of a particular use case? And as I mentioned, the ideal case is running real data, real problems, real users, but that's a very costly process because you can't really do experimentation on real life systems that much. Sometimes it's not ethical to do, and sometimes it's just not feasible to do. So we need to have better experimental settings for evaluating interpretability. So UCI is a wonderful repository for testing out or trying out new machine learning models or new machine learning techniques that we come up with. So there's this repository of great benchmark problems that help us compare different machine learning techniques. We need something similar for interpretable machine learning as well. And that traditional ML benchmarks that we use is not good enough for that. So we need some way to simulate a real problem. We need some way to simulate real data, some way to simulate real people. So there's a huge open area in figuring out what those experimental setups are and how can we design those test beds. And finally, we need proxymetrics to quantify the quality. So what is that? What does that look like? Can we come up with an equivalent precision or a recall or accuracy or F1 score for interpretability? Can we develop metrics like that that actually is a proxy for how good the explanation method is at helping some human being do better at a certain task? So those are very broad open areas that exist in this space, mainly related to evaluating explainability side. Evaluation of explainability remains an elusive topic. There are several ideas, several approaches proposed, but it remains to be seen how it progresses in the future. Yeah, so if I can continue for like 5 minutes, one thing I would encourage you all to go and read this paper. Hypoxemia. So this is one user trial that I mentioned that has real data, real users, and a real problem that they tested out SHAP, the method that Dr. Damayanti presented before, on the ability to help a doctor make certain decisions. So the use case is, so this is one of the very few, maybe I've only seen 2 of these studies done before to actually evaluate these things in the real world. So the use case is during a surgery, they're trying to predict whether a person would have hypoxemia. Hypoxemia is lack of blood oxygen, whether the oxygen level would drop during the surgery. So what they do is every minute, I think they make a prediction of the risk for the next 5 minutes, or every minute or every 5 minutes they make a prediction for a period of time, how much of a risk there is. So anesthesiologists are the ones who will consume this prediction and the explanation. They name the system pre-science. So as you can see in this figure, there's a prediction score 2.4, and there's an explanation why that 2.4 came to be. Normal pulse is green, that is good. Low tidal volume, that contributes 1.4. 1.9 high BMI, and when you add those things up, you get 2.4. That is the deviation from the average, that average score. So what they did, they wanted to see whether the system that they built pre-science helped anesthesiologists make better decisions. Can they actually identify hypoxemia risk better when they have the assistance of pre-science? So they did these comparisons. So they told anesthesiologists showing the data, right, to make the decision alone, given their expertise, make a decision. Then they have the models prediction, which is the pre-science alone, and they have the combined one. So anesthesiologists making the decision with the aid of pre-science, machine learning model, and score and the explanation. And they actually show that anesthesiologists make better decisions when they actually help with the system. So you can see the ROC curves here. So on the left, it's initial. Let's just look at the right one. So they have 2 prediction tasks. I'm talking about the real-time one. The green is the anesthesiologist making decisions on their own. The blue line shows the anesthesiologist actually help using the pre-science prediction and the explanation to make a decision. So clearly, it's outperforming the just using the data and making a prediction. So clearly, their system is helping them. The pre-science alone, the model alone is even better, but you can't deploy a machine learning model completely in a very critical setting such as surgery. So you have to have a human in the loop. So the blue line is the best actual case. Can anyone see a shortcoming of this setup from a perspective of evaluating explanations? I'll give you a minute or so. Anyone? Is there a problem with this setup? So spoiler alert, yes, there is, right? So they're comparing data alone, so the person alone, and person plus the ML model and the explanation. Our goal is to isolate the impact of the explanation. We don't know whether this benefit comes from the machine learning prediction or from the explanation or the combination. So we can't isolate the effect of the explanation with this setup. Ideally, what they should have done is have anesthesiologist plus the model score, then another group anesthesiologist with the model score plus the explanation. So that would have helped us to isolate the effect of the explanation. So we only know that the combination of ML score and the explanation is doing better. We don't know what the impact of the individual components, the two components are. So this was a great opportunity that they had to evaluate how SHAP alone performed, but they weren't able to evaluate that because of a shortcoming in their test setup. So designing these experiments is not trivial. So it's a very interesting research area where you can combine statistics and machine learning to design these experiments and perform these evaluations of interpretable ML methods in a real world setting. We are actually running one experiment these days. Hopefully that will get published in the next year. If that is the case, if you guys are in touch, should be able to share those things with you as well. So that's kind of it from what we had. Thank you very much for paying attention. I know it's a Saturday morning, so it's not the greatest of times for listening about machine learning predictions. I hope the introduction and the demonstrations that we had about different methods and the discussion afterwards gave you a sufficient enough knowledge about this area to start doing your own research and diving deep into these things to learn more and explore more. This is a very interesting research area. This is a very interdisciplinary research area as well, because it puts statistics, computer science, mathematics from a method development side, and then you have social psychology or like cognitive scientists coming in from a humans perceiving these explanations. You have human computer interaction where you actually how does the person interact with the system, the machine learning system, and how do you optimally present these things to the users. So it's a very interesting area. So, and feel free to contact us with emails. I've written down mine and Dr. Amarty's emails here. So please feel free to reach out, add on LinkedIn or anything. I'm on LinkedIn, and happy to help out if anyone is interested in pursuing some research in this area. Oh, nice. We have a question. What would be suitable tools, methods for interpreting sequence-to-sequence models such as neural machine translation models? That's a great question. So sequence LSTM models, if I'm not mistaken, right? I think currently layer-wise relevance propagation kind of stands out for a neural network specific thing. Check that out. It's LRP. It's what it basically doing is it's basically decomposing the neural network's function through a Taylor series and actually back propagating the important scores back to the input layer. I haven't personally tried it out with an LSTM or a sequence-to-sequence model myself, but I've run it with MLPs and they work really well. LSTM can be looked at as a very deep multi-layer perceptron, so hopefully it could work on that too. but it'll be interesting to see whether model agnostic methods such as SHAP or LIME would help you in that area as well. So please, please check that out. I hope that helps. Any other questions? All right. I think that's it from us. Dr. Damayanti, is there anything else?
Yeah, Dr. Gaston, I think we can wind up the session for today. So I'll invite Isara to do that.
Awesome. Thank you very much.
Thank you very much, madam, and thank you, Dr. Kassan. It's beyond doubt that today's event was indeed an insightful one that kept our minds whirling throughout. Therefore, once again, I would like to thank all the resource persons for joining us today. And we have prepared a virtual token of appreciation for each one of you to express our sincere gratitude. Dr. Kasun Amarasinghe, Mr. Shyaman Jayasundara, and Mr. Amila Indika. Thank you very much for your immense support and contribution to the tutorial. And a special thank goes to Dr. Damayanti Herath for organizing the event. With that note, we have reached the end of today's event. And I want to mention that please feel free to share your feedback with the shared feedback forms in the chat. And thank you very much for joining with us and have a nice day. Thank you, everyone.
Thank you.